Today we will discuss about time-based generator. This is the second part of fifth unit. In the first part of fifth unit, we already discussed about multivibrators. Okay, this is completely second part, time-based generator. So what is meant by generator? Generator is nothing but it generates some output signal, time-based signal. So based on, with respect to time, generators generates some signal with respect to time. Okay, so let us see. So it is an electronic circuit which generates an output, either it may be voltage or current, that changes linearly with time. That changes linearly with time. That means, suppose this is the time. For example, this is voltage. This voltage changes or increases linearly with respect to time. If time increases, then voltage also will increase. That is the meaning. Okay, that varies linearly with time. The waveform of the output should be a ramp. So this is the ramp signal. Okay, ramp signal. The main application of such ramp voltage is in CROs. Mainly we are using is these time-based generators in CROs. In practice, there are two kinds of sweep generators. Okay, if we take this voltage with respect to time, that is voltage sweep generator. This is time-based. These time-based generators are also known as sweep generators. Okay, another name for time-based generators are sweep generators. Okay, if we take in y-axis voltage, those are called voltage sweep generators. If current varies linearly with respect to time, then those are called current sweep generators. First one is voltage sweep generator, and second one is current sweep generators. Okay. Next, this is the general waveform of sweep generator. Okay. Two voltages V1 and V2. Suppose the waveform starts from V1 and ends at V2, and similarly it increases linearly, also it decreases linearly, and it settles for some time, and after that again increases linearly and decreases linearly. The time at which, this is the time at which the output waveform starts from initial to reach its maximum value, starts from initial value and reaches to maximum value. The time taken to reach the waveform starts from initial value to maximum value, that is called TS. TS is nothing but sweep time. Okay, we can define sweep time is the time at which the output waveform starts from initial value to reach its final value. That is called sweep time. Similarly, it again reaches to its initial position from here to here. This is the initial position. This is the starting position. See, both are same. Okay. The time next. This is called return time. How can we define return time? The time during which the waveform returned to its initial value. The time during which the waveform returns to its initial value is termed as restoration time or flyback time or return time. Okay, this is the sweep time and this is the return time. So how we can draw the different types of ramp waveforms. Let's see. This is another type of sweep waveform, and this is called sawtooth waveform. Sawtooth waveform. Okay, in this sawtooth waveform, there is no return time. Okay, why? Because it after it reaches to maximum value, it suddenly drops to initial value. Okay, it could not take any time. Just suddenly drops to initial value. So that means there is no return time. So TR equal to 0 in this case. Next, let us consider triangular waveform. This is triangular waveform. So it has TR. In this, TR is less than TS. For this particular case, TR is very much less than TS. Okay, this is the general waveform of time-based waveform. This is the general time-based waveform. Okay, next, deviation from linearity. Okay, this is also known as general characteristics of time-based generators. In your syllabus, the first topic, general characteristics of time-based generators. Okay, this is also called the time. Deviation from linearity. That means this is the linear signal. The output is we can get the output is not perfectly linear. It can deviate like this, it can deviate like this. Okay, that means it can be different from the expected value. Okay, we can get different waveform from the expected value. That is called deviation from linearity. Deviation from linearity. In general, the signals generated by the time-based circuits are not perfectly linear. The deviation of a signal from linearity can be described in terms of three types of errors. This error, actually we need this linear waveform, but we're getting this type of waveform. Okay, this is called deviation. This error is called deviation. It deviates from actual value. It is called deviation. There are three types of deviation errors. First one is sweep error, second one transmission error, third one is displacement error. Deviation from linearity. Three types of errors: sweep error, transmission error, displacement error. Okay. In the first one, sweep error. Sweep error. This other waveform. Output voltage, time t. The signal waveform will be like this, somewhat exponential, not perfectly linear, somewhat exponential signal. Let us assume this is Ts, maximum voltage Vs. Okay, so this is sweep error or slope. This is first one is sweep error. Okay, sweep error, slope error or sweep error. This is also known as slope error. Slope error, we can write it as ES, slope error. Slope error equal to initial slope formula minus final slope by initial slope. Okay, this is the slope error formula. ES equal to initial slope minus final slope by initial slope. Okay, initial slope, that means ES equal to slope. How can we define slope? dvs by dt. Okay, initial means at t equal to 0. This is a vs waveform, so dvs by dt at t equal to 0 minus final slope. This is also dvs by dt at t equal to final time ts, t equal to ts by initial slope dvs by dt at t equal to 0. Okay, how can we define sweep error or slope error? It is defined as the ratio of difference between initial slope to the final slope by initial slope. Okay, this is the definition and this is the equation. Initial slope and this is the final slope. The exponentially increasing voltage is mathematically expressed as, this is the exponentially increasing waveform, so it is mathematically expressed as v into 1 minus e power minus t by rc. Okay, why? Because we know that for exponential signals vs equal to, or output voltage equal to v final minus v initial into e power minus t by rc. We can write it as like this. Okay, this is the 0 up to it has to reach v. Stick, this is the 0, it has to reach final value is v. Okay, then final value of the waveform is v minus initial starts at 0 into e power minus t by rc. Okay, then v is the common, then 1 minus e power minus t by rc. Okay, this is the exponential waveform equation. Okay, where rc is the, this rc is called time constant. Time constant. Okay, differentiate with respect to, but we need these two equations, initial slope and final slope. First differentiate with respect to dt. dvs by dt equal to v into this value 0 minus e power minus t by rc into minus 1 by rc. Okay, otherwise do like this, just Vs equal to V minus V into e power minus t by rc. Expand this complete equation, multiply with V. Okay, then differentiate with respect to V, sorry, differentiate with respect to t on both sides. Then this is constant, so 0 minus V into e power minus t by rc with respect to t into minus 1 by rc. So dvs by dt equal to v by rc into v into minus plus e power minus t by rc. Okay, but we need initial slope dvs by dt at t equal to 0. Then v by rc e power minus t value e power 0, so that equal to e power 0 value 1. So you will get v by rc. This is the initial slope. Similarly, final slope dvs by dt equal to at t equal to ts. Okay, at t equal to this, then v by rc into e power minus ts by rc. This is the initial slope, this is the final slope. Substitute these two slopes in this basic equation. Okay, then es equal to initial slope v by rc minus final slope v by rc into e power minus ts by rc by initial slope v by rc. Okay, the v by rc common, so v by rc will be cancelled, and finally we get e power minus ts by rc. Okay, e power minus ts by rc. Condition: if ts is very much less than rc, then e power minus ts by rc is equal to approximately 1 minus ts by rc. Is the standard equation. If ts is very much greater than rc, then we can write e power minus ts by rc as approximately equal to 1 minus ts by rc. Then finally we get s equal to 1 minus ts by rc. So 1 1 cancel, then finally ts by rc. This is the slope error or sweep error, s equal to ts by rc. Okay, this is the first equation. Slope error, first error, slope error or sweep error. Just first draw the sweep error exponential signal, and then write the definition. Slope error equal to initial slope minus final slope by initial slope. For that equation, dvs by dt at t equal to 0 and dvs by dt at t equal to ts by initial slope. Therefore, exponential signals, we know that vs equal to v into 1 minus e power minus t by rc. After that, differentiate with respect to t. Then after that, apply initial condition and final conditions. So substitute these two equations in the basic formula. Okay, then apply this condition. If ts is very much greater than rc, then e power minus t by rc can write as 1 minus ts by rc. So then finally we will get s equal to ts by rc. Okay, next, second error, second one, transmission error. Transmission error, transmission error, e suffix t, we can write it as e suffix t. Okay, transmission error, e suffix t. This is the waveform t p. This is the linear waveform, but we will get deviation like this. While transmitting, the waveform will be deviated like this. This is vs up to here, this is vs, and up to this ramp, this is vs dash, that means this is input signal, this is output signal. Okay, vs dash is the input and vs is the output, but actually we have to transmit this, but at the output section we will get like this. This is the waveform. Next, Et equal to, we can write it as, it is difference between input to the output by input. It is defined as the ratio of difference between input and output to the input. Et equal to input minus output by input. That equal to input, we can write an input is Vs dash minus output is Vs by input Vs dash. Okay, where Vs is exponentially increasing signal. For exponential increasing signals, you know that Vs equal to 1 minus T by Rc. Okay, 1 minus T by Rc. 1 minus e power minus T by Rc equal to, if we expand exponential signals, 1 minus T by Rc plus T by Rc whole square by 2 factorial minus T by Rc by whole cube 3 factorial up to so on. If you expand like exponential signals, this will be like this. Okay, just neglect higher order terms, then we will get 1 minus minus into minus plus T by Rc minus T by Rc whole square by 2. Neglect other terms. 1 cancel. Just let's take common T by Rc. T by Rc is common. Then 1 minus, here another T by 2 Rc. Okay, this is the value of just 1 minus e power minus T by Rc. Okay, then Vs equal to V into 1 minus e power minus T by Rc. 1 minus e power minus T by Rc value will be this. Then we have to multiply with V. Vt by Rc into 1 minus T by 2 Rc. This is Vs value. Okay, this is Vs value. Next, at t equal to Ts, this is the time period Ts. Okay, this is Ts. At t equal to Ts, small vs equal to capital Vs. Okay, signal Vs. Then waveform Vs equal to capital Vts by, this is on also small Vs. Okay, then Vs equal to Vts by Rc into 1 minus t equal to Ts. So Ts by 2 Rc. Okay, this is the Vs value. Next, this is Vs value. Next, the input waveform is ramp waveform. Okay, the input is ramp waveform. So we can written it as Vs dash. Vs dash equal to, for ramp signals, alpha t. Standard equation for ramp, Vs dash equal to alpha t, where alpha is slope of the ramp. Okay, slope of the ramp. This one, this input signal. The input signal will be ramp. This input signal, this will be ramp. For this ramp, this ramp. Okay, this alpha t. Alpha is the slope of the ramp. Okay, but from the equation, slope equal to, that means alpha equal to V by Rc. Okay, slope alpha equal to V by Rc. Then Vs dash equal to V into T by Rc. V into T by Rc. Similarly, at t equal to Ts, this is small Vs dash. Small Vs dash equal to capital Vs dash. Okay, then substitute capital Vs dash equal to V into Ts by Rc. Okay, alpha equal to V by Rc, Vs dash equal to, this is slope value. Okay, like this. And finally, we get transmission error Et equal to input. This is the input V into Ts by Rc minus output Vts by Rc into 1 minus Ts by 2 Rc by input VTS by RC. Okay, VTS by RC is common and it will be cancelled. So finally we get 1 minus 1 minus 1 minus TS by 2 RC. Okay, this VTS by RC, VTS by RC common and will be cancelled. So 1 1 cancel. So finally we get TS by 2 RC. This is the transmission error. ET equal to minus TS by 2 RC. Okay, this is transmission error. Similarly, third type, displacement error. Displacement error we can define with E suffix D. Displacement error. Okay. This for this waveforms like this input signal deviates like this from upper side. Okay, voltage. Okay, this is half waveform, that means TS by 2. This is at TS. Okay, this is VS output. This is VS dash. We will get this point, maximum deviation and maximum difference between input and output we will get at TS by 2. Vs minus Vs dash, Vs minus Vs dash. At this point we will get maximum deviation. Okay, maximum deviation. This is the waveform voltage and time. Displacement error ED is defined as the ratio of maximum deviation to the sweep amplitude. Maximum deviation to the sweep amplitude. So we will get maximum deviation at Vs minus Vs dash max by sweep amplitude is Vs. Okay. After solving, similarly, like that, we saw after solving, we will get like this. ED equal to displacement error TS by 8 into RC. Okay. The remaining solution I will provide the PDF form. Just go through that. So ED equal to TS by RC. We will get like this. This is ED. Okay. First one, sweep error equal to TS by RC. Second one, transmission equal to TS by 2RC. Third one, ED equal to TS by 8RC. Okay, these are the three differences, three errors, or you can define the three characteristics, general characteristics of this one. Okay, and then how can you define the difference between or relation between ED and S? Relation between ED and S. ED equal to, we know that TS by 8RC, but T by RC equal to ES. So we can write it as ES into 1 by 8. Similarly, ED equal to, in terms of ET into 1 by 4. Okay, this is the relation between displacement and sweep. This is the relation between displacement and transmission. Okay, this is the general characteristics. The next class we will discuss about bootstrap and Miller circuit. Okay, thank you.